our special seminar today. So we have Alcides to talk to us about sequence of elements. So take it away.
Thank you, Tristan. Thank you for the invitation. Thank you very much. I'm happy to be here. Very nice city, and very nice place. So, okay, so I'm going to talk about, Tristan already said, nuclearity of certain sister algebras. And this is indeed it's a way to write sister algebras in a certain dynamical way, so to say, in a very generalized form, I should say. It involves also either a group, underlying group, or more generally a groupoid or an inverse semigroup. So this also has to do with nuclearity of algebras that we assign, or sister algebras assigned to those objects like groups. So maybe just recall, so we are going to work with sister algebras. So these are algebras of operators on a Hilbert space. And just a quick definition or recall. So we say that A is nuclear if we can, in a certain way, approximate this algebra by finite things. So in this case, finite dimensional algebras. So we say, just write here small diagram. So we look at the identity map. We can approximate this here by a sequence of maps. And they are not homomorphic, but they are sufficiently nice maps. So they are what we call CCP maps, so completely positive, contractive maps, such that, in a sense, so these approximate the identity. So this diagram doesn't commute, but it approximately commutes. So this converges in norm for every pointwise. It converges to the identity. Yeah. So this is the definition, and there are many. There is an important characterization here, and this is already a result. Yeah. So the theorem by maybe Hirschberg, I don't know, maybe other people, I don't remember. So, but one way to characterize is to say, so there is a unique norm on the algebraic you look at the algebraic tensor product. So you look at all the sister algebras, so another algebra of operators, and you can look at the obvious product and turn this into a star algebra. And then there might be many ways to complete these two again to a sister algebra. So of course you need for these norms. And there are cases where there is a unique norm. And of course, this is a very special case. And in this case, we say, and it exactly captures this finiteness condition. And there is always indeed a maximal norm. And there is always a minimal norm. And so this means that these are the same for every sister algebra. Okay, and this class of nuclear sister algebra is what appears in classification theory. It's one of the main assumptions that people make, to the algebras that we really can understand, classify, are usually in this class. So, but there are also sister algebras that are not nuclear, of course. So and every finite dimensional, almost by definition here, is nuclear. And one can prove that every commutative is nuclear. And then there are constructions that preserve this. So let's talk about groups. So a very nice class of sister algebras one can assign come from group. And in this case, one can characterize nuclearity. So say here is a discrete group. And then we can assign to it a sister algebra we look at, in this case, it's a discrete group. So we look at the L2 space of this set. Yeah. So, and then we take the bounded operators, and there is so-called left regular representation of the group that acts on the delta elements, or the autonomal basis here, used by the multiplication of the group. So we call this left regular representation. And so this then you can also extend to the group algebra, but at the end, so we can just take the closure of this and call this the reduced sister algebra of the group. So it's just the span closure of these operators. This indeed forms a representation. So this, without the closure, is a star algebra, and then you complete this to a sister algebra inside the bounded operators. Yeah? This is the so-called reduced sister algebra. And you can do this for, as you can notice here, for every other representation of the group, unitary representation. This is by unitary operators. So one can, in general, also assign the maximal sister algebra. Is essentially, you take the group algebra and you choose a sufficiently big representation. So the maximal, essentially the universal representation, there is one that captures all other representations, at least in norm. So there is indeed a maximal sister norm on the group algebra. This is also a sister algebra, but here this is not any more concrete. So it acts on some Hilbert space that usually we cannot describe. But of course, there is a certain map. We can view this. We usually confuse this lambda. This extends to the full sister algebra, and this gives a quotient map from the full to the reduced. Yeah? So when, of course, we would like to know, maybe like here in nuclear case, we have this nice situation out where this both maximal and minimal thing coincide. So we expect that something here happens. So these is a result by many people. Again, old result. I cannot name names here probably, but there are many ways to characterize when this here is equal. So this is indeed has to do with nuclearity. So the following are equivalent. So yeah, so this is indeed equal. So we write isomorphic via lambda. It can be actually any isomorphism if and only if one of these sister algebras and then both is nuclear. It is stronger to say that the reduced sister algebra is nuclear, but at the end they are equal, so both are nuclear and they coincide. And this has to do with some approximation property on the group, as happens for nuclearity. We can transpose this essentially to the group. So G is what we call as amenable. And amenable means many things, but maybe the definition from amenability means that there is a G invariant min. So this means that there is a state on the L infinity space. So state means essentially the same thing as I had before here for these matrices. It's also one of these nice maps. It's positive. In this case, it's a unito map. So positive unito. Yeah, and that's, I think, is already, and norm is norm one. So such that this also should be invariant. So we use the same representation. Now we can act by the same formula on functions, and then this should be invariant. So for every function and for every group element, so this is what you say, it's an invariant min. You can also phrase this in terms of a measure on the group and so on. So let me there are many, many different ways to characterize amenability. Is one of the notions that has maybe 100, more than 100 different characterizations. maybe not better, maybe 5,000. Okay, one of them is there is a so-called almost invariant vector. So we can look at the finitely supported functions. We can look in the again in the L2. So unit vectors such that they are almost invariant for the left regular representation, meaning that approximately, so there is a net, I should say here, such that this converges to 0. So we say there is a almost invariant vector. You can prove easily that the group, this representation has an invariant vector only if the group is finite. But in general, there are groups, many amenable groups. This is again related to sister algebras. So finite groups are amenable, and commutative groups are also amenable. But there are many others. And another way that I want to phrase this, instead of taking, this is of course the L2 norm, one can take the inner product. This is the same condition but written differently. So you can take the L2 inner product and look at these combinations here, and these go into 0 since these are unit vectors. So the norm, the inner product here of the same terms is equal to 1. So this is the same as saying that this here converges to 1 for every G. So I want to emphasize this condition because it will appear in a more general version later. And there are many, many other ways. So there is also, in terms of von Neumann algebras, so one can also look instead of the sister algebra, it's another sister algebra, but we can take the weak closure, and this is equal to the double commutant inside the bounded operators. This also has some property. This is what we call it von Neumann algebra is injective. So this means that there is a projection, a norm 1 projection from the bounded operators onto this von Neumann algebra. And injectivity is also something that is related to nuclearity, as you see in this result, of course, in this case at least. But it's the correct notion of nuclearity in the world of von Neumann algebras. There are also different characterizations. Yeah, but you should view this as an approximation property. Okay. Okay, so let's move now to other more general situations. So the idea is, how do we get more general examples? Of course, these give examples, interesting examples of nuclear sister algebras. Later in the 1980s, the 87, sorry, the 80s, from the 87, Claire Anataraman de la Roche came with a generalization of amenability that applies to groups acting now on sister algebras. First, in the 80s, she came with a definition for von Neumann algebras. So as you see from the beginning, so as I said, this is something about in the group about a state, which can be rephrased in terms of a measure. So it's natural that von Neumann algebras appear naturally here. So and she first defined what means, let's take a von Neumann algebra. So von Neumann algebra is just a sister algebra that is equal to the bicommutant. Yeah. So in particular, this algebra is, for instance, always unital, and it's weakly closed. And here by this I mean an action by automorphisms of the von Neumann algebra. So we say that this action is, let's say, von Neumann amenable. we sometimes also say Anandarama de la Roche amenable in honor of Claire. So if it's essentially taking some of these characterizations, so we can think about the definition instead of looking at state. We take a m-valued function that will replace the invariant measure, and this will be like again, so a map here. Maybe I should call P because it's indeed a projection, because you can view M inside here, and this will be indeed a G invariant projection. But maybe, yeah, why not? Yeah. So yeah, maybe P. There will be another P maybe later, so I didn't want. Yeah. So, but this is maybe I call it just phi. So phi is now not it's still positive. Norm 1. So it's indeed a projection. It's one of these maps again. So it's we could say is a CCP map, unito, unito and completely positive. So it's positive and also positive to matrices, such that it's phi is G. Now we should not say invariant because it carries a non-trivial action. We say equivariant. So equivariant means there are natural actions around. So here we can act with the left regular representation, but we have to also act here with sigma. So this is the diagonal action, and this should be equal to this. So lambda G sigma is just lambda G tensor sigma G, let's say, the diagonal action from the left regular representation, or sometimes we view lambda also as an action, as is happening here. And this is the definition, okay? And this is the definition for, so if can you see here? Maybe better to use there, because there is not so good, right? So it's like the German style here. Okay. Any questions you have so far? Yeah, so in this case, you can view just as functions, bounded functions from G to M, because G is discrete. In general, if G would be locally compact, for which there is also a theory, then it's slightly more complicated, and you take measurable functions and mod. Yeah, but in this case, just functions from G to M, bounded. Yeah, bounded. And this is also von Neumann algebra again. Yeah, the basic example is free group. The basic example of a non-amenable group is a free group, non-abelian. Yeah? So you take a free group with two generators. This is the basic example, and this amenability of group, it was invented by von Neumann, I think, and was called also Messbar in German, and has to do with measures. And I think he already noticed that the free group is not amenable. It's related to this Banach-Tarski paradox. Yeah, so amenability is really interesting subject. And the amenable groups, they are groups that are somehow approximable by finite things. Yeah. Finite. There are many ways to characterize this by these Follner sequences, for instance, or nets. Yeah.
Sorry, what was delta or something? Sigma?
At sigma, yeah. So this is the notation for my action. Okay. And then I just inducing some, say, the left regular representation up to here somehow, but putting together sigma. So this is just the action that does concretely the following. Yes, it's state this. So you take a function, then you act here by the inverse as the left regular representation, then you act by sigma. This is just another action, natural action that you would consider in this algebra. And okay, and then another definition now for a sister algebra and an action, let me call it alpha now, sister algebra action. The definition is slightly more complicated. So you could think maybe, oh, maybe let's do the same. So I still, everything that I wrote makes sense. I could act for a projection here, but this turns out to be not the correct thing to do. So this is not good. So what we do instead is there is always a way to assign a von Neumann algebra to a sister algebra. So you can imagine, because every sister algebra is already concretely represented in some Hilbert space, so you can concretely there take the von Neumann algebra generated. So what you do is you take the universal von Neumann algebra. So this is indeed, as a Banach space, just the universal von Neumann algebra. Every other von Neumann algebra is a quotient of this. As a Banach space, just the double dual. You can think in terms of representation. You take the direct sum of all GNS representations, and then you take the bicommutant. You can induce by dual action here of the group. Just bidualize the action. So we can use that this is now a von Neumann algebra. So this actually, I should say, is amenable, or sister amenable, if this is von Neumann amenable. Okay, and it turns out that there is a theorem then proved by Claire that this captures exactly what we need for nuclearity. So yeah, so in general, so if yeah, what should I say? So maybe I just talk about the sister algebras. So for instance, yeah, so this action is amenable. So one can get similar conditions to the theorem that relates amenability of groups. So there is a net. So a net as before. So we had functions on G. There it was just scalar functions. Here we take with values in the algebra. But this would be too strong, or maybe, yeah, it's not the correct thing. So you see here, we can go also to the bidual in general. And actually, it's important to take the center. So the things that commute with everything. So you take the center of this algebra, and you ask for a net here, which is, again, so just, so if you take the L2, the natural L2 A valued or A2 prime valued inner product like you do in L2. So this is bounded. So the norm here is 1. Yeah. The L2 norm, so I should say, yeah, for every I. So the point is that this is in the ball, it's bounded. And the second condition is the most important condition, is this condition here, so that we can write essentially the same. Now we put sigma here, and we use, instead of the scalar inner product, this inner product that naturally appears here, and this converges again to 1. It should converge to 1. But now we are in a sister algebra. We can ask about norm convergence, but we are also in a von Neumann algebra. And the correct thing to take is the weak convergence. So in the weak topology or strong topology, it doesn't make a big difference because the nets are bounded here. Okay, and if And maybe the second theorem is that, moreover, what is the so-called cross product, the reduced cross product, which is the analogo of the reduced group sister algebra. So there is a very similar way to build a representation of, now if A is represented on H, you represent the group inside there. So there is a way to represent this there. I don't have time to explain too much, but there is a nice sister algebra we can assign, which is the so-called cross product, the reduced cross product. This here is nuclear if and only if. So this is necessary that the algebra is nuclear for this to happen, and the action is a manual. So this exactly captures nuclearity of the sister algebra that we would like to attach in if we start with an action. Okay, so now maybe let's move then to cell bundles. So what is a cell bundle? I probably need to specify. So again, we take a Hilbert space. Yeah, you should look at cell bundles as some types of generalized actions of some sort. Yeah, there is some dynamics going on here. So let's take, say, a group to start with. And we look now at certain subspaces, just closed. So this is like a definition. Yeah, what is a cell bundle? Closed subspaces. This is more like a concrete cell bundle already represented. And since we have just closed subspaces, they are not algebras, but they have some nice properties. So if you multiply two of them, you should lie inside the product underlying the group. Yeah? And also, if you take the involution, this not necessarily is inside the same, but you connect this with the inverse of the group. Yeah. So this is concretely what it is, a cell bundle. Just that. So, and you can create like a cell bundle from an action. This is a very basic example where all AGs are just A, and you like use the action to create the subspaces such that when you make the product, you lie in the product here, in the lying product. This uses the action, and it's used in the same way as this representation, more or less, is defined.
You're saying only inclusion of A, being an H, that doesn't equality then follow?
It follows, yeah. You could also write equality because it's an involutive method. Yeah.
Did you just say that does every algebra actually be right for both of them?
Yeah, that's true. So maybe you know a group ring or group algebra or skill group ring like this, yeah. So you should just have an algebra and a group action. This is always graded, yeah. So what I'm talking about here is like a graded algebra. You can view this as a graded for a certain algebra. You take from here, you can of course generate a sister algebra by taking products of all these things. This will generate a sister algebra inside here. This algebra will be, in many cases, graded. Of course, I don't assume here in this case they are linear independent, but if they are, then this is essentially a grading. So it's one way to think of this, but there is a deeper interpretation for cell bundles, which a cell bundle is indeed actually some sort of action. If you replace, I was talking about actions by automorphisms. If you change the category a bit, so if you relax what should be the morphisms in the category of sister algebras, you can also talk about bimodules, yeah, or Morita equivalences, if you know this. And a cell bundle, actually, these subspaces here, they will be Morita equivalences between certain ideals of a certain sister algebra. So I didn't say observation here is that the unit fiber, if I take the unit of the group, is a C-star algebra when I have this, because A1 times A1 is in A1, A1 star is in 1, 1. So this at least is a C-star algebra. And you should view a Fell bundle as an action, a generalized action on this C-star algebra. Okay, and these other gradings here, the subspaces, they are bimodal. So they are certain types of generalized automorphisms. Yeah. Say again. Yeah, so I try to explain now. So C-star algebras of Fell bundles, as I said, so if I already concretely represent the Fell bundle here, I could generate a C-star algebra. There is a more intrinsic way to do this. So one can forget the representation, one can just take so-called compactly supported or finitely supported, in this case, sections. You can view this as just as algebraic direct sum of these fibers. So you disconnect them, so to say, you put them in a linear independent form. They may be here where they were not linear independent. So, and then you can use these products that we have here, because these give products between these fibers, what we call the fibers. So we can define here, if I have some element living here in the G fiber, and if I have another element living in the H fiber, I can use this product that I get from there to define a product on these generators. And using, of course, the group product. And in the same way, I can define an involution by just taking this involution and taking the involution in the group. So this is indeed a star algebra with this. It's obviously a vector space. So we can, as before, complete in two ways. One is the full C-star algebra. This is just, there is, in this case, a maximal, the biggest C-star norm possible on this. And there is also the so-called reduced C-star algebra, which is a concrete C-star algebra that will represent, now I need to maybe slightly generalize Hilbert spaces. This is a Hilbert module. So you just take, as I said, these are actually modules. So if you take a certain completed direct sum, you get Hilbert modules, and this is a Hilbert module over the unit fiber. In a very natural way, I can define here the inner product. So if I take two, so this is just the completion of the same space here, I should say, maybe just the completion with a certain inner product, just called 2 maybe, yeah, or maybe with values in A1. So it's just, we take like, the most canonical thing. So you look at finitely supported functions or sections, and then you do this here, you see from this condition, this is in AG star, this is in AG, so this will belong to A1. So this is in the same subspace, it makes sense to sum. So this belongs to A1, and this defines a nice inner product, and then you can complete this and canonically represent again via some what we call the left regular representation of the bundle. And then later in 97, there was a definition of an approximation property for these Fell bundles. We say that or Rui Excel defines A, this file bundle over a group has the approximation property, I just call AP, yeah. Has the approximation property if there is a net again. So we can think now with finite support with values in the unit fiber. Now it's not a section as above, it just takes values in this sister algebra such that, yeah, so we can define still the same type of formula as above. So I call this L2 norm. This is exactly the same formula as here. So this is bounded in norm. Yeah, so this is the supremum over I is smaller than infinite. So it's L2 bounded, a net. You don't need to ask this to be unit, to be bounded by one. Not necessary. Includes the condition. The important condition is that if I now take psi I, G, okay, I think it's GA, something like this. So if you now take the sum over age in the group, I fix some G, and I fix some element A from the fiber AG. These are living in the unit fiber, so it makes sense to sum these things. So they all live in the fiber over G. So we can ask this to converge in norm to this element. This should hold for every element of the group, for every element of the fiber over G. That's it. And this you should view as a generalization of this definition here. I didn't, I think I already erased. Here, this here. You should view this condition here as something, some generalized form of this thing here. Maybe I can even give a notation here. Yeah, so just a notation for this would be like an interpretation would be something like this. Viewing file bundles as some sort of generalized actions. Of course, this doesn't make sense because I don't have an action actually, but this I can define as this, and this should be indeed viewed like something like this. But there is an extra term here, so that we should put here. In general, one can also put an element of the algebra here and ask it to converge to A instead, and it turns out to be equivalent. Observe some important thing is also, we don't assume this to be central. And here it was assumed to be central. Yeah. And this difference is indeed the difference that we either put A here or not. So if you ask to converge to 1, it's necessary to put the center. So if I put A and ask it for every A, I can forget the center. So this turns out to be equivalent. It was not clear for a long time, but it turns out that we proved this recently. Okay, sorry. Yeah, true. Yeah, of course. Yeah, so it was designed to capture nuclearity of the cross product. Yeah. So in every group, even free group, not every group, but every nice group, say the free group is not amenable, but it has many amenable actions. So actually the so-called exact groups, a free group is one of those. Every exact group has by definition actually, or if and only if it has an amenable action on a commutative unitary sister algebra. So this was indeed designed to sort of get nuclearity, yeah. So to know how, yeah. Indeed, so there's a very important point. So the group need not be amenable. Still, the action might be amenable, yeah. And essentially every group has an amenable action. Actually, every group has an amenable action if you allow non-unitary algebras. So the translation algebra, the translation action on C0 functions on the group is always amenable in this sense, for instance. Yeah. Okay. So I want to mention this result, yeah. So by Excel already, it was proved in the same year that that if A is nuclear, A1 is nuclear, and the fell bundle has the AP, he proved that this implies that the full system algebra is equal to the reduced system algebra, and this is nuclear. So actually, there are two separate statements. You don't need to assume that A1 is nuclear for equality, but you need to assume it to be nuclear. Okay, so this is the analogous statement that we had for groups. This here, the converse is still open question. It's not known, even in very simple situations. There are partial converses, but I don't have time to talk about this. This is what we call the weak containment property. Whenever the full and the reduced are the same, we say the fell bundle, the action, has the weak containment property. So amenability or approximation property always implies the weak containment. It's not clear whether the converse holds. Yeah. We proved much later, was in 97, the same year he defined this notion. Very recently, I think it was around 2020, so joint works with Ferraro, Abadi, and I should also mention here my other work with Siegfried Eckinghoff and Rufus Willett, that also does essentially this for actions. So we recently proved that, yeah, in this form, so it's still open if I don't assume nuclear, but yeah, maybe I phrased this wrongly. So what is really open is whether just this equality implies the approximation property. If the reduced system algebra is nuclear, we could prove indeed that A has the AP. So this nuclearity again is captured exactly by this type of approximation property, which I should say, of course, for actions, these notions, when you start with an action, you look at the fell bundle, amenability in the sense of Nataraman de la Roche is the same as the approximation property for the fell bundle. So these are closely related equivalent notions. Now, how much time do I have? Like,
Well,
yeah, okay, good. So now I'll try to generalize this further.
So the nuclear one, I think that the reduced could be given to the maximum.
Again?
So the reduced could be nuclear, but that doesn't necessarily imply things.
This implies this was already also proved by Rui already, that if this is nuclear, if the reduced system algebra is nuclear, was already proved by Rui. You can prove that they both are equal.
Right.
And later, much later, we proved that actually this implies the approximation property. The approximation property was already proved by Rui that always implies the weak containment. What is not clear, even in very simple situation, even if you come from an action, the weak containment alone is not clear whether this implies amenability or weak approximation property. Under certain conditions, one can prove some partial results, but it's still unclear in general. It's a very hard problem, it seems. Any further questions? Okay. So let's move now to I think I don't have too much time. Inverse semigroups. Maybe I want to also relate this to groupoids. So we want to go a step further and consider Fell bundles also of a groupoid and inverse semigroup. So a groupoid, the shortest way is equal to the small category with inverses. So every morphism is invertible. Yeah, so the abstract definition of a category is a set with a composition where every element is invertible. We want also to consider étale. So this means that G carries a topology, and of course all the structure should be continuous as usual. And also, if I have a category, I have the objects, and I have the source and range maps. These are X to be local homeomorphic. This is a short definition of what an étale groupoid is. And from a groupoid, so we also always assume that G0 is a nice space, locally compact in Hausdorff there. And one can define essentially, this is not really the continuous functions, but if the whole space is Hausdorff disease, so you can think of this as the compactly supported continuous functions. And this is again a star algebra. You can define a product like before, and then one can complete to again the maximum and some reduced star. Okay, I don't have too much time to define this. So if I have an étale groupoid, I can talk about the so-called bisections, which are open subsets for which the source and the range, I guess it's enough to ask one of them to be injective. So local homeomorphism means that it's locally injective in particular, a bit more, as locally is injective and homeomorphic on its image. So we have many of those. So indeed, if the groupoid is étale, if and only if this is very large, so to say, so there's a basis, we always have a basis for the topology of the groupoid coming from this type of sets, these so-called bisections. And these bisections, they form an example of what we call is an inverse semigroup. So I can multiply using the groupoid operation by just multiplying whenever I can multiply. So this gives a multiplication on this set. So I can take any one of this set and multiply in this way. I just multiply the elements that I can multiply. And this is again a bisection, one can prove. And also, of course, we have the inverse, which is just the pointwise inverse. And this is again a bisection. This is what we call an inverse semigroup, which is just a semigroup so it carries a multiplication, but it has some sort of inverse. This inverse is only partial in a sense. So for every element of the inverse semigroup, there is a unique inverse, sometimes also called involution, so denoted by either the inverse or the star. There is a unique element for which these and these holds. And you can really think, if you like groupoids, how inverse semigroups can be represented as bisections, not all bisections, but a subset. You can of course take a subset here that respects this operation. You get again an inverse semigroup, and every inverse semigroup can be represented in that way. Okay. And if you notice my definition of cell bundles, we can again define in a similar way cell bundles or actions. Of course, we can again define actions or cell bundles. We can also talk about amenability of groupoids and inverse semigroups. This gets slightly more complicated, but still some of the results that I had for groups before can be proved, like the groupoid is amenable in a certain sense that you can define if and only if this sister algebra or this is nuclear. So in both coincide. It's still an open problem again whether the coincidence actually, sorry, it's not true actually. There are examples where this coincide, but the groupoid is not amenable. So they coincide, but they are not nuclear. Yeah, there are examples like this. So for groupoids, and similar for inverse semigroups, amenability is already much more complicated. So groupoids, they in particular include actions of groups on spaces. And more general, you can also consider the so-called partial action. You can act partially and still define groupoids. So, and one could also talk about actions of groupoids, but I go directly to cell bundles. So I can define again, so I go directly to the inverse semigroups, because these are maybe more general. We can define in the same way what's a cell bundle. We can think that, again, it's the same as for groups. They are closed subspaces. As before, we ask, so ST is containing ST, so we have the operation. We still have this pseudo inverse, so it makes sense to also ask this, or the star. Sometimes I write star, sometimes I write inverse. It's not really an inverse in the group sense. And there is a further condition here. So there are relations here. So they cannot in general be linearly independent as for groups. So there are indeed many inclusions. There is a natural partial order that you can think here as sets. So as I said, every inverse semigroup can be represented as sets like this. So, and this is just the inclusion in this sense. So in general, this just means that if I restrict T to S, this can be algebraically represented in this way, okay? This is an important condition that appears here and also causes problems. Okay, if I want to now define the sister algebra, there is a way, so I could proceed as before. I can still look at the algebraic direct sum. Yeah, so all elements here are elements like this. Yeah, so delta elements, so a function or just an element of this fiber. And of course, I can do as before. I can still multiply those, and this is what I want to do, of course. I can still define the involution. Because I have the involution on the inverse semigroup, but I also want to incorporate this relation. And in this space here, they are linear independent, so they do not incorporate. So what we do indeed, we take a quotient. Yeah. So we look at this here. We quotient by the things that the differences of things. So I want to identify this with something like this. So I take the difference if I take S smaller than T, and if I take something in the fiber which is smaller. So it makes sense to talk about A delta S and A delta T. And I want this to be equal. So I mod out by the ideal generated by these differences. Actually, the span is already an ideal, you can prove. And then you can, again, take this. There is a certain maximal C-star norm, and that's what you define to be the maximal C-star algebra of the spell bundle. You see, it gets more complicated because of this relation, but you can still define. And similar, we can define the so-called reduced C-star algebra. Yeah, so when actually it gets more complicated here, but the idea is essentially the same. We want to take a certain representation in this Hilbert module, but we want to again implement this relation. So, and because of that already he appears biduals for Neumann algebras. So actually you can only represent this in a certain bidual for Neumann algebra or for Neumann module. So to say this is a bimodule over the unit fiber, I should say here, I assume without loss of generality that I have the unit in the inverse semigroup. And it's possible to define this. And the point is, there is a certain inner product that maybe I should define here, because this has to do with the approximation property that I want to define. So I want to do the following. What I want is to do like, I want a priori, I can like try to sum everything a priori. This is not the correct thing to do, but I can start doing like attempting to define an inner product here. So I could start summing over, if I have finitely supported sections, now I can try to sum this, but this is too large. So what we do in the group case is we only take the diagonal and then we sum over the diagonal. Yeah, S is equal to T. And here, so we can maybe put this here like this. So we want to take the product into account. So we do the product here, and we want to put this somehow in here. So this is just the product of the algebra, but I want to get an element here. So what we do, there is a way. So this might have something inside, so something smaller. And it might have something smaller which intercepts the unit here. So there is a certain projection I call unit that exactly does this job. So it projects this thing in the fiber, intercepts with this part here. So it gets slightly technical, but you can define this. And this turns out to be an element not of A1, but of the double dual. Yeah. So for Neumann algebras actually naturally appear here. Maybe just, can I have just some more minutes to define and then have the theorem? So we came then with the definition of the approximation property. So we say that A, this spell bundle, has the AP. So this was in this recent work by me and Diego Martinez in 2023, this year, already published. So if there is, again, a net of, I should write here, sections from S, I'll explain this here. So you take the cell bundle, you can restrict to the idempotent and pull back to the inverse semigroup back. So this means the idempotent, things that square is equal to E. So this is idempotent part of the inverse semigroup. This here just means that if I apply a certain S, this will be in the fiber, in this fiber. this is contained in A1. So these are functions from S to A1 you can view, but they have prescribed value in certain ideal. This is always an ideal in the algebra. So there is a net. Again, this net is bounded as before. This is the first condition. So, but bounded here resembles this condition here. So again, we take a certain sum, double sum, but we project down to a certain, by a certain project. Actually, there is a small thing here that there is a commutation relation and has to take into account. So it's not really that, but almost the opposite. One can move this also here to the middle. And if you move this to the middle here, this exactly forms this projection that is there. Okay, this is the first condition. And the second, I want, as before, to write something like we had for action. Yeah. So I want to put something like this. Yeah, S, say. So here S. But this is again gets slightly more complicated. So we have something like this. As for groups, we would like to sum like ST. Let me write what I would like to have here, but it's not correct. So then we want to put S here, and then psi T here, and we would like to just sum over T, and want this to converge to AS. Yeah, we want this to converge to AS in all. But then again, in the inverse semi-group, we have these relations, these inclusions. So this turns out to be not, this was our first attempt. We just took this definition and tried to prove things, but it didn't work. So what you have to do again is to rewrite this sum by summing something like every R here, and then you need to put a certain projection here to correct this sum, which is too big. So it's a projection that is something like ST star, I guess. Yeah, there is a certain projection you should put there. Maybe, yeah, I think it is correct. So this is the definition. Maybe, yeah, if I can, like right here, maybe. The theorem is the same. So if A has the AP, then first the full system algebra is equal to the reduced, so has the weak containment. And if the unit fiber is nuclear, then these both system algebras nuclear. They are equal and nuclear. So that was the main point. So we get for this huge class of system algebras that include group points, inverse semi-groups, actions, and so on. We have this general condition that implies nuclearity. We couldn't, or still didn't work hard to prove the converse, but it should also hold that the nuclearity of this algebra should imply the AP, but we didn't write it yet. Thank you. I think I'll stop here.
So, yep.
Definition of the KCI?
This R is a variable. So you sum.
No, sorry, the other. And the KCI. Oh.
These are
Other
here.
definition.
Okay. This is, yeah, good. Forget this. Yeah. So this is just a notation, but this just means I look at functions from S to A1, which are finitely supported, has compact support and this condition. So this notation was just a way to write this. You can forget this. So you just have functions from S to the unit fiber satisfying this condition. So this notation was a pullback along the idempotent part of the Fell bundle, pulled back to the inverse semigroup. That's what we are doing, right? So this notation of R that I had here is meant to be this here. So it's like a pullback.
Yeah.
But the R here appears 2 times, so it's maybe better to avoid this R.
And also you mentioned that, okay, if I understand correctly, that every inverse semigroup is a subset of the bisection of some groupoid.
Yeah.
And then if we start from a groupoid and then a subset less like S inverse semigroup there, and then is it related to such as AP to also the original groupoid? Because
Yeah, it's related. So there is a nice duality, but you need to take into account more structure. Yeah. So if you start with the groupoid, you can look at the bisections. This is always an inverse semigroup. You can take any sub-semigroup here. It's again an inverse semigroup. Okay. And of course, it's possible to recover G, but not just from S. Yeah. So actually, there is the inverse semigroup. It acts on the unit space of the groupoid, and the action is very natural here. So if I take one of these U here, and I want to X at some unit, you just take the unit because these are bisections. So this is injective. So if there is at most one element here that I will find with where I can put this here. So, and this in this case has to be the source of G. So this will be indeed the range. And this has to be the source of G. So there is a natural action of the inverse semigroup on this space. And you can recover the original groupoid from this action. And the amenability of the groupoid is amenability of this action that you can transform in a Fell bundle and apply this definition. That's one of the results that we prove. So
but
more or less, yeah.
which definition of the amenability for groupoid?
Yeah, so yeah, I didn't have time to explain, but it's very similar to the group. You can sort of use the same definition that we had here, but forget the bundle, yeah? So in the groupoid case, it will be much simpler here. It will be a sum that we have. Yeah, we will have a functions, a net of functions. And here, in the groupoid case, I can really write as in the group case. It will be something like this here. I sum over H. I take, there is a net for which finitely or compactly supported in the topological case, for which this converges to 1 then. So it's the AP for a certain Fell bundle. Yeah, there is also, I didn't have time to discuss this, but there was a previous definition of the approximation property for Fell bundles over groupoids by Julian Krantz, and he proved similar results. And our definition, of course, was also based on that, and we proved that his AP is equivalent to our AP. If we start with a Fell bundle with a groupoid, there is a way to build a Fell bundle of an inverse semigroup, and these both share the same AP property. And the AP property for the groupoid itself is the same as the AP property for this action. Yeah, it's a lot of information in it, but sort of. I hope it answers your question. It's a groupoid. Yeah, so you can also view like, instead of an inverse semigroup, I would have maybe a groupoid here, yeah. You can sort of define the same sort of thing, but it's maybe better not to represent this because some of the fibers, they are quotients of other things. So it's maybe just say that I have products, yeah. So what I'm giving here by these representations is indeed, I give products and I give involutions like this, yeah. So a Fell bundle abstractly, I didn't define, but abstractly, a Fell bundle is just a bunch of Banach spaces over some object that has a product and an involution, like a groupoid, and the product behaves well with the product in the involution in the underlying object. Now, if you have a groupoid, you also have a topology. Then this should be also varying continuously. So we also ask that these are in a certain sense continuous, but this is essentially the same definition. And for groupoids, we don't have this because they are already, we took fibers, so to say. The difference here is that these here, they represent several elements. And here we take just single elements, so to say. This looks very much like the group case. And the inverse semi-group is more general. Yeah, exactly. Yeah. It's just a continuous or upper semi-continuous bundle over the base space is a groupoid, and there are multiplications and involutions between certain fibers. Of course, here I need to assume here that this is multipliable here, the groupoid case. Yeah. It's a good question. Still open question, actually. So as I said, for groupoids, Julian Krantz defined this, he studied this. He proved a sort of converse or a sort of result that partially answers your question. He proved that if the C-star algebra, he didn't prove this in general, but he proved that if you start with an action of the groupoid on a C-star algebra, an action, I would need to define this, but an action is a very special type of Fell bundle. If you start with this special type of Fell bundle, and if you ask the corresponding cross product, the full or reduced to be nuclear, he proved that the action is what he called measure-wise amenable. In this word, as you see, some von Neumann algebras start appearing, and it's not clear whether this measure-wise amenability is equivalent to the approximation property. It's known in some cases, like I think for actions on commutative C-star algebras, it was already proved by Anaterraman de la Roche and Renault, but in general, we don't know. But I expect this to be true. So if this here is nuclear, I expect the Fell bundle to have, even over inverse semi-group to have this approximation property, but we didn't work hard yet to prove this. It requires more work, and this would give this result also for Fell bundle over groupoid.
I guess more broadly wondering to what extent the teacher of the completion remember the groupoid.
So another type of question, yeah. It forgets many things if you don't give further structure, even for groups, yeah. So you have like, you have two groups with 4 elements for which the C-star algebra are the same, and it's C4. So it's for finite groups, essentially only remembers the order. For finite abelian groups, yeah, essentially only remembers the order of the group. So if you don't have further structure, you can forget, you cannot capture. But there are, of course, results if you add more structure, like if you remember here that this is actually a quantum group, for instance. This carries a co-multiplication that comes from the multiplication, and you can completely recover the group. And there are versions also for groupoids. There's another result, like if I know the C-star algebra, and if I know the commutative space, and it sits inside there nicely, we say maximal abelian, and there must be some other conditions, there must be a projection. So if you add more structure, you can indeed recover the groupoid back from this. But you need more structure. It's not just the C-star algebra.
Okay. Questions? Oh, yeah.
Question. So if you generalize from discrete in another direction to something continuous, I don't know, SU2.
That's a good question. So we also did work for groups, at least. I mean, for groupoids also there are notions of, you can certainly also define this AP here for topological groupoids. Julian didn't write these, but essentially the same definition carries over. For inverse semi-groups, we usually don't consider topological inverse semi-groups, but for groups already, we did a study for topological groups, yeah, locally compact. The locally compact groups, they are the ones that we can assign sister algebras. And then we have a definition of amenability, and this was not clear from Claire's, so this was a big step. So she only defined amenability for actions on von Neumann algebras for topological groups, but when she came to sister algebras, she didn't. And the reason was this bidual thing. If the group acts on the sister algebra, you can bidualize the action, but this is too big. If the group is topological, the action here will not be nicely continuous in general. So you need a special quotient of these that we call how do we call this? A certain von Neumann algebra, which is a quotient of the bidual. And there is where essentially the biggest sister algebra that carries a nice action. So it becomes much more technical, but we did indeed define study amenability, and we proved many results also recently, and prove like nuclearity and many other permanence properties. And we also found examples, I think SL2R or something like this. We found examples of sister algebras for which the weak containment holds, but the action is not amenable. So if you extend this to locally compact groups, we have examples. Yeah. But then you need to carry the topology of the group, of course, is important. Yeah, a group as a discrete group might be non-amenable, might be amenable as a topological group. Every compact group is amenable, and every amenable group acts amenably in every sister algebra.
Yeah, I think it's a good. Let's thanks.